Hi, my name is David Held, and today I'm going to talk to you about my research on perceptual robot. So a robot typically consists of a perception system and a planning and control system. Now, typically researchers are also divided into these categories. We usually have vision researchers as well as robotics researchers that work on each of these systems separately. What I'd like to propose is having perceptual robotics researchers, and as a question, can we build a better system by thinking about both of these parts of the robot together? Now, to clarify, I'm not proposing that we merge perception with planning. I'm just proposing that we should think about perception and planning at the same time. Now, why is it that we would need to think about both of these parts together? First, let's ask the question, why can't roboticists just use the output of a computer vision method as input to their system? Well, let's look at what computer vision methods typically produce. Here are some typical examples for object detection and segmentation tasks. And we can see that the main goal of computer vision is to understand what is in an image. On the other hand, the main goal for robotics is to understand what will happen if a robot interacts with its environment. So, for example, if a robot takes an action to interact with this cloth, we want to be able to predict what will happen so that the robot can determine what actions it needs to take in order to produce the desired effect. Okay, so from another perspective, we can ask, why does most current work today focus only on perception or planning and not both? Well, I believe that this is because of an assumption that many robotics researchers have that one day our perception systems will be perfect, perhaps with some small amount of Gaussian noise. And so if you believe this assumption, then a reasonable plan would be to build better perception systems. Simultaneously, we can design planning methods assuming near perfect perception. And then one day we'll connect the components, hope for the best, and maybe it will all work. Now, this approach, this assumption about perfect perception might be true in the factory when we know what's coming down the conveyor belt, but it won't ever really be true in the messy real world in which we live due to many factors that will inevitably cause perceptual errors, no matter how good our methods might one day become. And so what I spend a lot of time thinking about is how do we bridge the gap between imperfect perception and planning? So for example, suppose that the robot sees this crumpled towel. How should we represent this towel to enable a robot to manipulate it? There are different possible representations, and they might have different properties in terms of how easy they are to learn and how appropriate they are for a given task. So my goal is to learn to manipulate novel, perceptually challenging, and deformable objects. And I believe that this requires rethinking robot perception and planning algorithms to handle these types of objects and manipulation tasks. So today I'm going to talk about just two projects. The first will be about SoftGym, and the second will be about a graph-based dynamics model for cloth manipulation. So I'll start by talking about my work on SoftGym. This is work done led by my student Xinyu Liu. So a typical paradigm in machine learning is to collect a large image data set, input that data set to your favorite machine learning algorithm, and the algorithm will hopefully produce the output that you desire. These machine learning algorithms are typically trained for computer vision on a large computer vision data sets, such as the different data sets shown here. And these data sets have really driven forward progress in this field. Here you can see the performance on the ImageNet classification task. And you can see that every year, the performance gets better and better as new architectures are developed. And so these data sets have really enabled researchers to be able to see if they're making progress by being able to compare different methods on one standardized benchmark, which enables us to determine when one method is better than the other. Now, in reinforcement learning, instead of data sets, we have simulation environments. So here you can see the Majoko simulation environment. And you can see three different environments for the locomotion, for different locomotion tasks. Now, what I'm interested in is deformable object manipulation. Here you can see some images from recent papers on deformable object manipulation. And one thing you'll notice is that these different papers all evaluate on different tasks, simulators, and robot setups. And this makes it actually quite hard to compare different algorithms to see if we're really making progress on these tasks. Now, deformable object manipulation is quite important. It's used for a variety of applications, such as cooking, laundry folding, packaging, and manufacturing or repair. And it's also not easy for robots to perform deformable object manipulation due to a number of factors. First is the high-dimensional state representation. So as opposed to rigid objects, whose state can be compactly represented by just its 6D pose, deformable objects such as a cloth can be represented by, in the case of a cloth, it can be represented by a mesh grid with hundreds of vertices, each of which has a configuration that you would need to know to be able to represent the state of the entire cloth. Another difficulty is the complex dynamics. Here you can see a video of a cloth moving in different ways, and these motions are fairly complex and difficult for a robot to be able to predict. And finally, deformable object manipulation is difficult because of self-occlusion. So if you only saw this observation of this cloth, only some of the points in the cloth are visible to you, and many of the other points are occluded, and it's hard to know the full state of the cloth because you cannot perceive how the occluded points are folded underneath the cloth surface. So in order to drive progress forward in this area of deformable object manipulation, we've developed a benchmark known as SoftGym. This is built on NVIDIA Flex, and here you can see 6 different environments that we've developed for this benchmark. So these environments involve manipulating water, rope, or cloth in different ways. We call these 6 tasks SoftGym Medium. We also have 4 harder versions of these tasks in SoftGym Hard. And finally, we've released 3 tasks, or we've established 3 tasks that involve a robot interacting with these objects that we refer to as SoftGym Robot. The tasks shown on the left for SoftGym Medium instead have these 2 spheres that interact with the object that we call pickers. So they can pick different points on the object and move them. And so they abstract away the manipulation side from the robot's perspective and allow us to focus just on how the object itself should be manipulated to perform the task. Here you can see a comparison between actions being performed in the simulator on the left compared to the same action being performed in the real world on the right. And you can see that the effect of these actions is fairly similar between simulation and the real world, and this should give us confidence that any policies that we learn in the simulator are likely to transfer well to the real world. So on this benchmark, we have evaluated a number of state-of-the-art reinforcement learning algorithms. Here with this black line, I'm showing the performance of the of an oracle method. We call it the dynamics oracle. And this method uses the cross-entropy method, and it receives as input the ground truth state and the ground truth dynamics for all of the objects in the environment. So the ground truth state and dynamics are typically not available to the robot that needs to instead infer the state and estimate the dynamics. But just to get a sense of the upper bound of the performance, we evaluated this dynamics oracle. And here you can see the performance of a number of different state-of-the-art reinforcement learning algorithms that we've also evaluated on these tasks. So you can see, so I'm not going to go into detail about the performance of each of these methods, but what I will highlight is this method on the bottom left, spread cloth. You can see that each of the state-of-the-art methods shown in the different colored lines perform much worse than the performance of the oracle, showing that there is a large gap between the performance of these methods and what could actually be achieved by an ideal algorithm. So here you can see some visualizations of how the different methods perform. So here I'm showing the performance of the dynamics oracle for this task of transporting this cup of water across the table without spilling. And you can see that dynamics oracle is able to perform this task. On the other hand, one of the state-of-the-art reinforcement learning algorithms, in this case, I'm showing curl, spills water while trying to move it across this table. Here's another example where I'm showing the performance of the dynamics oracle on this task of spreading this cloth and trying to flatten it. And it is able to do a reasonable job. And on the other hand, on the bottom right is the performance of again, curl, which is one of the state-of-the-art reinforcement learning algorithms. And you can see that at the end of its episode, the cloth still remains quite crumpled. So why is it that the state-of-the-art methods perform so poorly on this set of tasks? For many of the methods, it's sort of hard to really understand why the performance is so poor, but we can actually analyze at least one of the methods. Here we're going to analyze Planet, which is a model-based reinforcement learning algorithm that uses a latent vector dynamics to predict the effect that its actions will have in the future. So here, so what we're going to do is visualize what the actual effect of the robot's actions are compared to the effect that Planet thinks its actions will have. So first, let's look at this task of pour water. So Planet is going to perform this sequence of actions, and you can see what actually happens when it performs these actions is that it's trying to pour water from one cup into another, and you can see that much of the water ends up getting spilled out of the cup. Now below, you can see the prediction. What did Planet think would happen when it performed these actions? And you can see that in this prediction, all of the water is perfectly poured from one cup to another without any spillage. Now, why is it that Planet did not predict the spilled droplets of water? It's actually quite reasonable when you think about it, because Planet is trying to minimize the reconstruction error between the predicted image and the true image. And these spilled droplets of water take up only a small number of pixels in the image, so it doesn't really incur much penalty in terms of the loss by not predicting them. Additionally, it's actually pretty difficult to predict exactly where these spilled droplets of water will be. So it's both a difficult task and doesn't contribute a lot to the loss. So Planet just ignores these spilled droplets and does fine in terms of reconstruction, but not very well in terms of the actual task of pouring water without spilling. Here's another example where Planet is trying to flatten this crumpled cloth, and you can see that the actions that it takes still leave the cloth in a fairly crumpled state with many wrinkles. On the other hand, here you can see the predictions of what Planet thought would happen after taking these actions, and you can see that the cloth is still quite crumpled at the end of this. You can see that that Planet thought that the result would be kind of this like flat orange blob, and again, it makes sense why Planet did not predict the location of all of the wrinkles, because the wrinkles take up a small number of pixels in the image. So predicting this orange blob doesn't really without wrinkles doesn't really give you a much worse reconstruction error. And additionally, it's quite hard to predict exactly where the wrinkles will be, so it's much easier for Planet to just ignore them. And so that might be fine from a reconstruction perspective, but again, if the task is to flatten the cloth, it's not so fine. So the main takeaway here is that Planet and many other state-of-the-art methods that use latent vector dynamics models tend to lose subtle but important details that are needed to actually perform these tasks. So in conclusion, we've introduced SoftGym, which is a new set of benchmark environments for deformable object manipulation. This benchmark should speed up research progress by allowing researchers to build on top of existing methods, develop new methods, and compare their new methods to previous methods. Additionally, we have analyzed a number of different state-of-the-art reinforcement learning methods on these tasks and proposed some ideas about why these methods might be failing to perform these tasks well. So that was my work on SoftGym. And next, I'm going to talk about our recent ongoing work on learning a graph-based dynamics model for cloth manipulation. So here we're going to start by asking the question, how can we learn a dynamics model for cloth? We have, let's say, this observation image of the cloth in some configuration. The robot is going to apply some action to the cloth, and we want to predict what effect this action will have. So how can we do this? One approach that we just discussed is to learn a latent space dynamics model. So we would compress this cloth into a latent vector. Then we will concatenate to this vector a vector representing the action that the robot will take, and then feed in these two vectors to a dynamics model that will predict another latent vector representing the predicted next state of the cloth. So this can sort of work, but as we saw, this type of model tends to ignore many of the important details of the deformable object. And essentially it's because a latent vector doesn't capture any inductive bias about the physical properties of the cloth. And so this type of representation tends to overfit easily. Another representation that could be used is to learn a pixel dynamics model. So given an image of the cloth in the current time step, we can try to predict an image of what the cloth will look like after some actions are applied. In our experiments, this tends to work better than a latent dynamics model, but it still doesn't get as good performance as we would like because a pixel dynamics model still doesn't capture the physical structure of the cloth itself. It only operates in pixel space. So our approach instead is going to be to learn a graph dynamics model over the estimated cloth mesh. So given an observation point cloud, we're going to estimate the mesh of the cloth and then use a graph neural network dynamics model to predict how that mesh will deform after the robot applies a given action. So why is it that we think a graph is a good representation for this task? Well, first of all, we should note that a cloth is often modeled by a set of points connected by springs. And so a graph can use different types of edges to model different forces that affect the cloth. So for example, we can have an edge for the spring force, we can have node potentials for gravity, we can have other types of edges for the collision force or for friction. So what are some challenges that we might face in trying to learn a graph dynamics model for cloth manipulation? So suppose that we have an RGBD observation and we extract from that a voxelized point cloud and we want to learn a graph dynamics model. The first challenge we might face is we need to understand how these points in the point cloud are connected on the underlying cloth mesh. So all we see here in the observation is just a set of points, but we don't know how they're actually connected to each other. Some of these points are connected on the underlying cloth mesh and some are not because of how they might just appear near to each other because of how the cloth is folded. So So that's the first challenge. And the second challenge is we can't even see most of the points that are part of the cloth due to self-occlusion. So we can only see a certain set of points that are visible to us on the exterior of the cloth, but we can't see the points that are folded underneath because of the self-occlusions. So our solution to this problem is first, we're going to learn to estimate how the visible points on the cloth are connected. And second, we will learn a dynamics model over just the visible points. We'll call this visible connectivity dynamics. And the main idea is that because we're learning a dynamics model, the learning process can produce a sort of intuitive dynamics model that learns to take into account the partial observability of the cloth. So let's see how that works. So we start with an observation of the cloth from which we extract a voxelized point cloud. So this voxelized point cloud will be the input to our system. Next, we can take nearby points in this point cloud and connect them by collision edges that are that represent the collision forces between nearby parts of the cloth. And then we can feed these collision edges into an edge prediction GNN, which tries to classify which of these collision edges represent mesh edges, meaning that these nodes are we predict that these nodes are connected to each other on the underlying cloth mesh. We can then input the collision edges and mesh edges into a dynamics GNN that will predict the effect that a robot's action will have on the cloth. We can then input this prediction back into our model in order to predict the effect of a sequence of actions. Okay, so let's talk about each of these components. So first, we have a voxelized point cloud, and we're going to connect points that are within a radius of r to each other via collision edges. So these points are considered to be close enough that they might impact collision forces on each other. So we connect them by collision edges to represent that. So this is our first graph is we have a node for each point in the voxelized point cloud and an edge for each of these collision edges. Okay, so given this graph, the next thing that we're going to do is to predict which of these collision edges are also mesh edges, meaning that we estimate that these points are actually connected to each other on the underlying cloth mesh. Not all collision edges will be mesh edges. Some points will be near to each other just because of how the cloth is folded, but won't actually be connected on the underlying cloth mesh. So to predict the mesh edges, we will use a graph neural network. So the input will be this graph where we will have a feature on each edge that represents that is the distance between the two nodes that edge connects. And then we will encode that graph, perform message passing, and then decode that graph. And the output will be a classification score between 0 and 1, which is our prediction of whether this collision edge is also a mesh edge. So that's the edge prediction GNN. And then given the collision edges and the predicted mesh edges, we will input this new graph into the dynamics GNN that will predict the effect that the robot's actions will have on the cloth. So in this case, for each node in the graph, we will have a feature to represent the node's velocity, as well as an indicator of whether the robot has picked that node to apply an action. And then we will, for each edge, we have an input feature, which is just the distance between the two nodes that the edge connects. And then the output will be the predicted acceleration on each node. So for the node that the robot is going to be moving, we know what the acceleration of that node will be, but we don't know what the acceleration of the other nodes on the cloth will be. So we use our dynamics GNN to predict the acceleration for the other nodes, and then we can integrate that acceleration to get a prediction for the points, the position of all the points on the voxelized point cloud. So that's our dynamics model. How do we actually use that for planning? So we're going to plan the robot's actions in the high-level action space. So the robot will pick the cloth at one point and move it to another point and then release the cloth. Now, instead of predicting the effect of this entire action in one shot, we're going to divide up this action into a sequence of waypoints and predict the effect of the robot's actions for each of these waypoints using the dynamics model. And then we will combine these predictions together to get a prediction of the effect of the entire pick and place action. So in order to plan to choose some good actions, we need a reward function to optimize. So in our case, we're going to be focusing on the smoothing task. So the reward function will be as follows. So for every point in the point cloud, we will imagine a sphere surrounding that point, and then we will project these spheres onto a plane and compute the total area covered by these projected spheres. So for smoothing, the goal will be to maximize this total projected area. So we use a pretty simple planning algorithm in this case, greedy planning, because this wasn't the planning algorithm wasn't actually the focus of this paper. So for greedy planning, we will just sample n different actions. We will score each action according to the reward based on the predictions from the dynamics model, and then we will choose the best action and perform that one. We train our method in simulation using the Flex simulator wrapped in SoftGem. We train just by performing random actions and using those to train the dynamics model. And we are able to easily transfer our model from simulation to the real world because we're using a voxelized point cloud as input to our method. So we take the point cloud in simulation, we voxelize it, choose a 1 point per voxel, and we do the same thing in the real world. So then the voxelized point cloud in simulation and in the real world have the same resolution based on the size of the voxel grid. And this allows us to easily transfer from simulation to the real world. Okay, so here you can see the performance of our method. On the top right, you can see the different actions that we are considering performing. And the actions shown in green are the ones that are predicted to have the highest score or the best effect. The ones in red are predicted to have a worse effect. And so we're going to choose the action that we think will lead to the cloth best becoming flattened. On the bottom right, you can see the predicted effect of what we predict the effect of the robot action will have on the cloth. So you can see how the graph is deforming. That's our prediction of what will happen if we apply this action. And on the left, you can see the effect that these actions actually have on this cloth. And you can see that the cloth is now much smoother and covering more area than it was in the initial state when it was more crumpled. So in terms of time, we'll sort of skip past this. So here you can see we also perform smoothing on silk. So it generalizes different materials and also to different colors because we just use a voxelized point cloud. We also compare our method to a number of different state-of-the-art baseline methods. And here on the x-axis, you can see the number of pick and place actions. On the y-axis, you can see the normalized performance. So our method shown in blue has much better performance than the baselines. Okay, so I think I will acknowledge the students who helped who led these projects, as well as our different sponsors, and I will end here. Thank you very much.